All right, subscribers, welcome back to another episode of Science with Surback. Today what we look at is sections 20.1 through 20.3, which introduces us to electrochemistry. Now, before we get into these details of these notes, I want to outline a few objectives that you should be able to meet by the end of these notes. So objective number 1, identify the oxidizing agent and reducing agent in an oxidation-reduction reaction. Objective number 2, balance oxidation-reduction reactions by the method of half reactions. And objective number 3, diagram simple voltaic and electrolytic cells labeling the anode, the cathode, and the directions of the ion and electron movement, and also the signs of the electrodes. So we get back here, and this is actually a review from our redox equations. And what we have to remember is two terms. The oxidizing agent is the substance that accepts that electrons, and the reducing agent is the substance that gives away the electrons. And so the easiest way to do this, the easiest way to identify the oxidizing and reducing agent is to go through an example. Okay, so what we need to find out is the oxidation number of each substance. So what I'm going to write down below this equation here is the oxidation number of each substance. Okay, so for elements in their natural state, like H2, the oxidation number would be 0. Now for O2, it's also in its natural state, so initially here the oxidation number is 0. Now once elements become entered into a compound, or they become chemically bonded, they begin to have those charge. So what I like to do is I like to divide that substance in half, and now sometimes you may have to divide it via the polyatomic ion and ensure you have the right charge of the polyatomic ion and go through it this process. But this one's relatively simple. So we have H2O. Now remember, if you look up O on the periodic table, you're going to find that oxygen under most circumstances has a -2 charge. Now we are looking for the charge of each individual 8. So remember, to find the charge of each individual H, we need to think, okay, what times 2, since we have 2 hydrogens, plus -2 would equal 0. Well, that would mean that hydrogen has a +1 charge. And I'm going to put this note out to the side here, and that is this. That this is the charge of each H. Okay? Now, hydrogen went from a 0 to a 1 charge. What that means is that it lost electrons. So I'm going to put this acronym out to the side here, right above our oxidation number. I'm going to put the term oil. And oil stands for oxidation. Oxidation is loss of electrons. Okay? So because we went from 0 to +1, we lost electrons. And so that means H is oxidized. It lost electrons. Now, on the flip side here, oxygen went from 0 to -2. So it gained electrons to become more negative. Now I'm going to put the acronym here, RIG. And that is reduction. Reduction is gain of electrons. So again, because oxygen went from 0 to -2, O, or oxygen, is reduced. Now, we get to this point here to actually answer the question, identify the oxidizing and reducing agent. Well, here it says the oxidizing agent accepts electrons. Well, O accepted electrons to become reduced. So this O is the oxidizing agent. That means H is the reducing agent. And so the key thing here is to identify the correct charges. And remember, it's good to review those particular charges to be able to identify what substance is reduced and what is oxidized. And ultimately, out of that, you can find the oxidizing and reducing agent. Now, before we leave this page, I want to emphasize why we did this or why we reviewed that. And that's because we get into this term or this concept of electrochemistry. And so electrochemistry is defined as the branch of chemistry that deals with the relationships between electricity and chemical reactions. And I'm going to add a little bit to that here. I'm going to put the flow of electrons, okay? So again, the key thing here, the reason that we need to identify where the electrons go is because that helps identify in our electrochemistry unit where is the flow of electrons, and that is really going to help us determine what happens going forward. All right, so we've spent a lot of time on this, but again, it's really important to identify where those electrons go. Now, let's review another concept known as half reactions. So half reactions are defined as an equation for either an oxidation or a reduction that explicitly shows the electrons involved. You can see that example that I show with tin 2+ and iron 3+. Okay, so we can split this whole reaction here into two different reactions, the oxidation and the reduction half reactions. Now, we've done this before, but what we are going to do is we are going to balance via half reactions. So what we need to do first, we need to split apart the oxidation and reduction reaction. Then we balance everything except hydrogen and oxygen. After that, we balance oxygen by adding water to the appropriate side, and then we counter out that water with H pluses on the opposite side, and then we balance the electrons. Now we do that for both the oxidation and reduction reaction, and then we multiply each half reactions so the electrons cancel or the electrons equal, and then we add and simplify if necessary. And then you always double check when we're balancing these chemical reactions. So again, keep these steps handy. You want to reference these as we go through this process. And so we'll go through a example. Now, I do want to point out too, and I probably should underline this, that this is for acids. Okay, so we have a chemical reaction that we want to balance via half reactions where we have the permanganate ion, MnO4-, and the oxalate ion, C2O4 2-, and it is in an acidic solution. So again, we always start out and we break apart these oxidation and reduction reactions. So we break apart MnO4- to Mn2+. Now, we don't need to write this down, but Mn here went from a 7+ charge to a 2+, so that means it gained electrons. This is our reduction half reaction. Now, our other reaction here is our oxidation half reaction, and that is C2O4 2- is getting oxidized to CO2. Now, we start out with one equation at a time, and it says balance everything except H's and O's. Well, the only thing we have here is Mn, or manganese, and they are balanced. So now we turn to our O's. So we have 4 O's on our left. What that means from our steps is that we need to add 4 waters to balance that out. So we have 4 H2O's. Now, on the other side of the equation, we have 4 times 2, 8 hydrogens. That means we need to have 8 hydrogens. And then we get to balancing our electrons. This is very crucial here. We have 8 times a positive 1. So a positive 8 plus a negative 1. So we have plus 7 on our left-hand side. And on our right-hand side, we have 2. That's a positive. Plus 0, so a positive 2. So we need to go from plus 7 down to plus 2. So the way in which we do this is we add 5 electrons, and that balances those charges out. Now, for right now, that is balanced. That's all we can do with our reduction half reaction. We move down to our oxidation half reaction. So this one, we have 2 carbons. We have to balance everything except H and O's. We have 2 carbons. We only have 1, so that means we need to put a 2 out in front. Now, we balance our O's by adding water if needed. So we have 4 oxygens, 2 times 2, 4 oxygens. Okay, so we're good. We don't have to worry about waters. We don't have to worry about H pluses here on our oxidation half reaction. But we do need to worry about charge. So over here we have a 2 minus charge, and over here we have a 0 charge. So we can only add electrons. So to make this balance, we add 2 electrons. Okay, so again, that's all we can do right now. And now we ask ourselves, okay, we have to multiply these reactions so that our electrons equal or eventually cancel out. So the first numbers that these meet at, 5 and 2, is 10. So what I'm going to do is I'm going to multiply the entire top portion by 2 to get to 10 electrons. So I have 2 times 5, which is 10 electrons, plus 2 times 8, which is 16 H pluses, plus 2 times 1 MnO4, the minus 1 charge. We have 2 Mn2 plus 8 H2O. Now, again, like I've done before, once I multiply something, I like to cross it out because I know I should not use that. Now, again, we have to get to 10 electrons. So to get to 10 electrons on the bottom here, I need to multiply that equation by 5. So I'm going to have 5 C2O4 2 minus, and that's going to go to 10 CO2 plus 10 electrons. Okay, so now everything is good to go. And again, I like to cross this out to signify that I'm done with this. And only thing that we can do here is cancel out our electrons. So our 10 electrons, because they're on opposite sides of the equation, can cancel out. So all we need to do here is add these equations up together. So what we would end up with is 16H plus 2 MnO4 minus plus 5 C2O4 2 minus, and that is going to yield 2 Mn2 plus 8 H2O plus 10 CO2. Okay, so now we move to the check for our balancing. So the first thing that I always check is to make sure we have the appropriate substances or the appropriate elements. So we have 16 H's on the left. We have 8 times 2, 16 H's. Those balance out. We have 2 manganese on our left, 2 on our right. Then we have, I'm going to skip over oxygen and go to carbon. 5 times 2, that's 10 carbon. 10 times 1, that is 10 carbon, so we're good there. And then our oxygens, we have 2 times 4, so 8 plus 5 times 4, that's 20. So 8 plus 20 is 28. Well, we have 10 times 2, 20 plus 8, that is 28. And now, another double check here is that your charges should balance out as well. So we have a charge of 16 times a positive 1, so positive 16, plus a 2 times a negative 1, so we're down to negative 14, plus a negative 5 times 2, and that would get us a positive 4. On this side, we only have 2 times a positive 2, so our charges balance out. We have a 4 plus charge on our left, 4 plus charge on our right. So there's actually a double check when we balance via half reactions. And that's how we would do it for a substance in an acidic solution. Now, one thing that we have not talked about, and that is what happens if we balance via a basic solution. So our steps look very, very similar, except this. Number one, I have this outlined in red because this is basic solution. So we're going to split our reactions into the oxidation and reduction half reaction. We're going to balance everything except H and O. Then we're going to balance O's by adding water. H's need to balance out by adding H+. We balance those electrons. And then we have this fifth step. It's kind of a weird step. And it says add the same number of OH minuses as H pluses added to each side of the half reaction. Now, again, that's kind of a weird step to see in our steps, but it will be shown in our example on the next page. Now, the remaining steps are the same. The only difference is we add in, hey, that OH minus has to be in our equation. And again, I think it's kind of a weird step, but we'll see how this works out. Okay, so it says balance this equation that takes place in a basic solution. And again, the problem should tell you if it's a basic or acidic solution. So what we do here is, again, we split apart the oxidation and reduction half reaction. And so I'm going to start up here with our Cn minus going to CnO minus. And this right here is our oxidation reaction. And so we split this other part into MnO4, 1 minus, and it goes to MnO2. Again, this is the reduction half reaction. You could split apart and find the charges, but that is the reduction half reaction. And we go through this as follows. So it says, first, we start out by balancing O's by adding water to the opposite side. So since we have 1 O up here on top, that means we need to add 1 H2O. Okay? Now, we have 2 H's. We need to balance out 2 H's by adding 2 H+. Okay? Then we balance out the charges. So on our left-hand side, we have a -1. On our right-hand side, we have a -1 plus a +2. So that's a +1. We need to get it down to -1. So what we do is we add 2 electrons. Now comes our weird step here. Because we're in a basic solution, we need to add OH minuses to each side, and the number of OH minuses need to equal our H pluses. So this means that we need 2 OH minuses on our right, and we need 2 OH minuses on our left. Now we go to this problem here. It says balance everything besides H and O. Well, they're balanced right now, and now we go to our oxygens. On our left, we have 4 oxygens. On our right, we have 2 oxygens. So we need to add an additional 2 waters on our right-hand side to get our oxygens balanced. Now we have 4 H's on our right. We need to add 4 H pluses to our left. Then we turn to our charges. So we have 4 times a positive 1, which is 4 plus a negative 1. That means we have a 3 plus charge. Over here on the right, we have a 0 charge. So we need to add 3 electrons. Okay? Now, our last step here, because we're an acidic solution, after we add the electrons, the same number of H pluses that we have to add OH minuses. So, because we have 4 H pluses, that means we need 4 OH minuses. I'm going to rewrite that so it looks better here. Again, you have to add your OH minuses to each side, okay? Now, I'm going to rewrite this even before I multiply my electrons to balance out. And that is because on each side, if you have an OH minus and an H plus, that forms water. So this top equation can just be written as 2OH minus plus H2O plus Cn minus. Nothing changes on the left. And now you can get CnO minus plus our H plus and our OH minus. They're equal, and they balance out together to H2O and then plus 2 electrons. So that makes it a little bit cleaner, a little bit nicer to work with. Again, once I rewrite something, I cross it out because I've already used it. Now again, your OH minus and your H plus combine together to form H2O. So on the bottom equation here, we would end up with 3 electrons plus 4 H2O plus MnO4 minus. That yields MnO2 plus 2H2O plus 4 OH minuses. Okay, so we've just rewritten it to consolidate our waters. Now, what we need to worry about is thinking about, hey, how can we multiply these equations so that those electrons cancel out? So what we do here, 3 and 2, they are going to meet at 6. So to get 6 electrons on my top equation, what I do is I multiply it by 3. So 3 times 2 is 6 OH minus plus 3 times 1 is 3 H2O plus 3 times 1 is 3 Cn minus yields 3 CnO minus plus 6 H2O plus 6 electrons. Again, once I use this, I cross it out. Now, to get to 6 down below here, this equation needs to be multiplied by 2. So I have 2 times 3, that is 6 electrons. 2 times 4, that is 8 H2Os, plus 2 times MnO4, which is 2 MnO4 minus 2 MnO2 plus 4 H2O plus 8 OH minus. All right, so we've got a lot of work And now we need to add these together. Our final step here, we need to add these two together. And I'm going to rewrite that. Okay, so what we need to do here, we need to consolidate before we start to add these things together. So first off, our electrons cancel, which is always good. Then we really need to think about this. We have 6 OH minuses and 8 OH minuses. Again, if it's the same substance on opposite sides of the equation, they can cancel. So all 6 of these OH minuses cancel out. We end up with only 2 OH minuses on our right. And then we have to be really careful with our waters. On our right-hand side, we have 6 plus 4. On our left-hand side, we have 3 plus 11. So what I'm going to do is I am going to do this. I'm going to cancel all of these H2Os out. And I'm going to cancel all of these H2Os out and cross this out to have 1 H2O. Again, that's because we had 11 H2Os on this side and we had 10 H2Os on the right-hand side. So we double check to make sure there's nothing else that can be canceled out. And we go ahead and we add our equation to solve this. So we end up with this. We end up with 1 H2O plus 2 MnO4 minus plus 3 Cn minus. That yields 3 CnO minus plus 2 MnO2 plus 2 OH minus. Okay, a lot of work. Now we need to double check. So we have 2 H's on our left. We have 2 times 1, 2 H's on our right. We have, I'm going to skip over oxygens. We have 2 Mn's on our left, and we have 2 Mn on our right. That's good. Skip over oxygen. We have 3 C's. We have 3 C's on our right. That's good. And now our nitrogens, we have 3 nitrogens and 3 nitrogens. So we're good. We check our oxygens. So we have 1 plus 2 times 4. So 1 plus 8, that is 9. Then we have 3 times 1, that's 3. Plus 2 times 2, that's 4. So 3 plus 4 is 7. Plus 2 times 1 is 9. So everything balances out. That's really good. Now, with oxidation reductions, half reactions, when we balance via half reactions, we got to make sure the charges are equal. So on our left, we have 2 times negative 1. So negative 2 plus 3 times negative 1. When we add those together, that's a negative 5 charge. Over here, we have 3 times negative 1, negative 3, plus 2 times negative 1. That's a negative 5. So not only do our substances balance out, but also our charges balance out. And that's what we're really interested in. And as we get further and further into this particular unit, those charges, following the charge, is going to be really important when we do some calculations. So that's a lot of work. I know it's a lot of things that we've done here, but that's how you balance via half reactions for something in an acidic solution and for something that is in a basic solutions. All right, so now let's really tie this whole business of oxidation and reduction half reactions to some of our electrochemistry here by defining some terms, and then we are going to label a diagram. Okay, so our terms here with a Voltaic cell. So a Voltaic cell is just defined as a device in which electron transfer occurs via an external circuit. Now, we call these things a couple of different things, galvanic cells And this is a spontaneous reaction. So when we put these substances together in the way in which we will here with our label, we will see that this is a spontaneous reaction. And more importantly, as we go through calculations, that will help determine what are our pieces and parts. Now, I'm just going to briefly go over these, but these are some terms we also need to know of here. The anode is defined as the solid metal in which the oxidation half reaction takes place, whereas the cathode is defined as the solid metal in which the reduction half reaction takes place. And then we have this third term down here, a salt bridge, and it's just defined as a saturated solution of electrolyte and is used to maintain the electrical neutrality of the solutions in both half cells. Basically what that's saying is, hey, we have to have some flow of ions as this process happens, and that's what that salt bridge does. And you can see here it allows anions and cations to move through porous barriers. Now again, electrochemistry and especially voltaic cells is important to determine what the flow of electrons is. So let's go ahead, keep these terms handy here. Let's go ahead and label a diagram so we have a better idea of what is happening. All right, so here is our voltaic cell, and we want to label all parts of the voltaic cell with a strip of zinc that is placed in a solution of copper 2 sulfate. Well, let's go a little bit deeper here into what this voltaic cell is. And I want you to just kind of cross some of this stuff out right now because we're not going to worry too much about it. We're going to concentrate here on what is labeled in our picture here. Okay, so what we need to think about here is we need to think about our strips of metal. So we have two strips of metal. Okay? And these strips of metal are going to be zinc and copper. Okay? So we have here our zinc. So I'm going to label this metal here as zinc metal. And we can call this solid zinc here. And over here, we'll call this solid copper. Now, I do want to use this here that it is placed in a solution of zinc sulfide, okay? Or sulfate, excuse me. So what is happening here is this. We are going to get these sulfate ions, and we're also going to get these zinc ions. Now this zinc is going to go up the salt bridge, which we'll talk about here in a second. And then on our flip side here, we are going to also have the copper 2 sulfate, so SO4 2 minus, as well as our copper 2 plus. Now, I'm going to draw an arrow and we'll talk about what's happening here in a second. Now, I want to talk about this. Zinc is going to be classified as my anode, okay? So zinc right here, this metal strip is going to be classified as my anode. That means we have a negative charge at the particular anode, okay? So I'm going to label this as a negative charge. And so what this also means here, because zinc is our anode, if we take a little look back on our definition, the anode is defined as the solid metal in which the oxidation half reaction takes place. Okay, so oxidation is loss of electrons. And so what this means is this. We would get solid zinc going to zinc 2 plus, and 2 electrons would happen here. And so I want to add just a little bit here to this. The anode is the oxidation half reaction. Now I want to talk a little bit about what is happening here with these electrons. So these electrons, this is connected via a wire. This is just a little wire. So these electrons are going to follow this wire here. They're going to go through this particular voltmeter, and they are going to go onto or be deposited onto our copper metal. Now, our copper metal, what this means about our copper metal is that this is our cathode, okay? So our cathode has a positive charge. Now, what is happening here at the cathode is the reduction half reaction. So that means here that copper 2 plus is being reduced to solid copper. So in other words, this copper 2 plus is gaining electrons. That's why we see the addition of those particular electrons. So I want to add this here, is that this right here is the reduction half reaction. Now, I want to talk just briefly about a few things that are happening here. I want to ask the question of this. Number one, which electrode will gain mass? And the answer to that is the cathode. The cathode gains that mass. Now, my other question here that I have right now is which electrode loses mass? And the answer to that is the anode. Now, before I ask my other two questions here, I want to talk about here my salt bridge, okay? So right here, this U-shaped tube is the salt bridge. And this salt bridge is just to help with the flow of electrons. And in this particular tube, you would have kind of a paste-like material. And let's say we have Na2SO4, okay? And so what would happen here is this. Our Na, our positive Na plus, would flow to this side here, and our negative SO4 2 minus would flow to our side with zinc, okay? And that is just to help flow with those charges. And again, we need that flow of charges to allow that electron to go from the anode to the cathode, okay? Now, I want to ask two more questions here on our picture here. Number one, which solution will increase in concentration? And the answer to that there is the zinc sulfate, so ZnSO4. Reason for this is some of the zinc metal is being deposited into this solution here, which is meaning we have a greater and greater amount of zinc 2+ present, which means that increases in concentrations. Now on my flip side here, what solution decreases in concentration? And the answer to that is the copper 2 sulfate. Again, why that is happening is because some of this copper 2+ is being deposited onto the copper metal to produce a greater amount of copper. Now, the last thing that I want to leave you with, I'm going to write it up above here, is the overall reaction here of what is happening, okay? So the overall reaction is going to be solid zinc is reacting with copper 2+ to produce zinc 2+ plus solid copper. That is our overall reaction. That is our overall reaction of what is happening here. Okay, so we packed a lot of information here. There's a lot of information here on this diagram. We took some time to label it. We identified the anode, which is the negative terminal, and the cathode, which is the positive terminal in our picture here, or our diagram here. And the last thing that I want to identify here is this. Notice how we have a big loop of charges that are carries, or a big loop of charge that is carried. So I want to emphasize this here. This right here, this voltaic cell produces a big loop of charges, okay? That charge gives us voltaic cell batteries. Now, the key thing about this is that we need to identify what is reduced, what is oxidized, to help be able to set this voltaic cell diagram up. All right, we put a lot into this. We've done a lot of review. We've added in those oxidation, reduction, half reactions via half reactions, or balancing via half reactions in both acidic and basic solutions. And we tied these concepts to our new idea here of voltaic cells. And when this happens here, this would produce 1.07 volts, okay? Now, next set of notes, we're going to learn how we can identify how many volts a particular oxidation, reduction, half reaction would produce in a voltaic cell setup. Hope you have enjoyed this video, and if you haven't already, make sure you subscribe.